to speak about the comparative planetology, that is, studying the planets and objects in the solar system by comparing one another, and emphasize the geology and the retention of atmospheres of the objects of the solar system. So if we begin with the largest objects in the solar system, the large outer planets, we have the gas giants and the ice giants, and the Earth there for comparison. We can see the size is substantial, and it has a lot to do with the retention of atmospheres. So in this diagram, what is shown is the temperature on the surface of a planet or moon in the solar system. And so what this means is if you are hot, it's because near the sun. The object is near the sun. So the first object here going from this way is Mercury. Then we see Venus, the Earth, Moon, Mars, Jupiter, Ganymede. There's this red dot we'll come back to, and so on. Saturn, Titan, Uranus, Neptune, Triton, and then finally Pluto. So distance from the sun is measured going out this way because this is temperature getting hotter this way. So close to the sun is on the far right, far from the sun is on the left. Now what else is on this diagram is the speed needed to escape that object. This is called the escape velocity. It's related to the mass and the radius of the object. Mostly the mass is what we are concerned with here because the densities of these objects are not too different from each other, but the masses are substantially different. So the speed you need to escape, what does that have to do with the retention of the atmosphere? Well, the speed you need to escape is how fast molecules need to move in the atmosphere in order to reach the escape velocity and leave. And if you think about it, molecules in the atmosphere, if they leave the planet, then they are gone and they don't come back. Or they leave the moon, they're gone and they don't come back. And so the objects as we see today will depend on whether they can retain an atmosphere and what kind of molecules. So these lines are very important. The dotted line along here, anything above here, this means that the object has a very high escape velocity, which means it's very high mass. We start with Jupiter, Saturn, Neptune, and Uranus, the four largest, most massive planets in the solar system. Then Earth and Venus. This line here corresponds to the limit of being able to have hydrogen in your atmosphere. And if an object can have a lot of hydrogen, it can be a gas giant. And this is what we mean by retaining an atmosphere, because hydrogen and helium are the most abundant elements in the universe. They are the most common and most abundant elements in the universe. 99% of all of the atoms in the universe are hydrogen and helium, and therefore if you can keep those atmospheres, the planet can grow to be quite big. And Uranus and Neptune, not quite as much as Jupiter and Saturn. The Earth, well, it can't keep those, and it is below that dotted line, but it's down here about where this solid line is, and below that we can see that we have the Earth, Venus, Mars, and then another dotted line, and then Mercury, Ganymede, and Titan, and the Moon, all about the same mass. Triton and Pluto, lower mass than that. So vertically we have the mass only the giant planets keep hydrogen and helium. That's what makes them giants. Starting Jupiter, Saturn, Neptune, and Uranus, that's what makes them giants. And so they're able to keep all of that hydrogen and helium. As far as the terrestrial planets, the Earth-like planets, if we can take a look at what they look like. Now this is a little different. Venus is covered with a thick atmosphere. This is not shown in this photograph, whereas the atmosphere is shown here. What's really shown here is the size, and we can see the surface. Now, this is because Venus is almost always completely covered by clouds because it has a thick atmosphere. So we see already that the larger of these have atmospheres. Mars has a very thin atmosphere. We can see a glow, a faint glow around the edge. Mercury, no atmosphere. And the other large object in the inner solar system, the moon, also has no atmosphere. So if we look how that works with this diagram, this region between the solid lines, and between the solid line here and the dotted line, are objects that can have some kind of atmosphere of oxygen. Carbon dioxide is the heaviest of the gases that could be for an atmosphere. Mars has a thin carbon dioxide atmosphere, and Venus and Earth. Now Mercury has no atmosphere because it's below this dotted line. But notice that if Mercury was located far out in the solar system, if Mercury was as far out as Pluto, then Mercury would have an atmosphere that could be as thick as the Earth's atmosphere. And so this is because this depends on the temperature of the planet or moon, how far it is from the sun, as well as how big it is. So if Mercury was at the distance of Pluto, it could have a thick oxygen, carbon dioxide, nitrogen atmosphere. Oxygen might require a difficult process to have on a planet that far away. If we look at the 7 large moons in the solar system, think also about the geology. We know about the geology of the Earth and Venus with volcanoes, Earth having plate tectonics, Mars having extinct plate tectonics, extinct volcanoes. Well, probably no plate tectonics in the past, but extinct volcanoes, and Mercury with extinct volcanoes. We see lots of geology, lots of things happening. All of these large moons are round because they have melted, they have differentiated. Differentiation is where a planet, a world, a moon, that has enough mass and it gets hot enough at some time, probably early in its formation, so that the heavy things sink to the bottom and the lighter things are on top. And so we can see the variety of light things on top here. Titan is the only one with a thick atmosphere. Ganymede, Callisto, and Europa and Triton all have ice on the surface, very low density material. Io and the moon do not have ice, and of all of these, the moon is the only one that doesn't have a significant geological process changing the surface. Actually, the moon and Callisto, neither one of those have much changing the surface, very old surfaces, but the moon also has no ice, Callisto an icy surface. So Callisto and the moon are similar in that way and different in the fact that Callisto is an icy surface and the moon is rocky. Io with the volcanoes, a very active place. So we can see that these large moons have a lot of activity. These large moons are also larger than any dwarf planet. The dwarf planets are shown here. We have Eris, Pluto, Makemake, Haumea, and Ceres. Ceres is the only dwarf planet in the asteroid belt. So all of these are icy objects. Pluto could be about 70% rock and 30% ice. Eris probably something like that, maybe a little more ice. So we see that compared to the Earth, these are all very small. The moon is 1/4 the size of the Earth, so the moon would be substantially bigger than any of these, and all of these are smaller than the large moons. Yet we also found that for the ones that we've seen up close, Pluto, Charon, the large moon of Pluto and Ceres also even has geological processes, vents coming from the interior and so on. But mostly also many craters indicating areas of old surface. So if we look at this again, finally we see that large moons and dwarf planets are above this line. The only one below it is the moon. And so this is because the moon is in the inner part of the solar system, and even though it's about the same mass as Titan, for instance, it cannot have an atmosphere, whereas Titan does have an atmosphere even denser than Earth's. So 2 factors determine whether an object has an atmosphere, no matter whether it's a planet, large or small, or a moon or dwarf planet. 2 factors: how hot is the planet, how far is it from the sun, and what is its mass, because the more massive it is, the more atmosphere it can keep, and the colder it is, the more atmosphere it can keep. So if we just look at a summary, we can see Venus, Earth is a little bit bigger, Mars, Ganymede, Titan, Mercury, Callisto, Io, the Moon, Europa, Triton, Pluto, and then some moons of Uranus, Titania, Oberon, Charon, Dione, moon of Saturn, Ceres, dwarf planet in the asteroid belt. Here's Enceladus. There are some others here that are in between that are larger than Enceladus, but I wanted to look at Enceladus here because Enceladus has been discovered to have water geysers or vents, and it even in this relatively small, or what we could call a medium-sized moon of Saturn in a very cold part of the solar system, it doesn't have an atmosphere, but it has geological processes, something going on inside, warming the water, causing it to erupt from geysers on the surface. So that's the conclusion of the comparative planetology and the retention of atmospheres and geology of objects in the solar system.